about complex eigenvalues in order to solve a system of differential equations. First, let's review some ideas from before about phase portraits for linear systems with real eigenvalues. Recall that we made the following proposition. Let's consider a two-dimensional system where we will assume that q does not equal to 0 and p squared minus 4q is positive. Here we can express p and q in terms of our 2 by 2 matrix A. First, the only equilibrium point, y sub 0, is the origin. Second, there are two distinct eigenvalues, lambda 1 and lambda 2, and they are both real numbers. Third, any eigenvectors v sub 1 and v sub 2 associated to these eigenvalues form a basis for R2. And fourth, the general solution to our two-dimensional system is capital Y equals k sub 1 times capital Y sub 1 plus k sub 2 times capital Y sub 2, where y sub 1 of t and y sub 2 of t are straight line solutions. We can use all of this to write down an algorithm that will help us to sketch the slope fields for a two-dimensional system. Step number 1, compute the eigenvalues lambda 1 and lambda 2, as well as the eigenvectors v sub 1 and v sub 2. Second, we'll draw a line in the direction of our eigenvalues v sub 1 and v sub 2 going through the origin, our equilibrium point. If lambda sub 1 is positive, we will place arrows on this line going away from the origin. If lambda sub 1 is negative, we'll place arrows going towards the origin. There's a similar statement about the second eigenvalues lambda sub 2, corresponding to the new direction for the new eigenvalue v sub 2. This will divide our plane into 4 regions. In each of these 4 regions, we can then sketch curves with arrows which follow in the direction of the arrows from the previous step. A plot of these curves is called a phase portrait, and a plot of the arrows is called a slope field. Let's say that both of our eigenvalues are negative. Then the origin is called a state. In particular, if v sub 1 is less than v sub 2, then all solutions will tend to the origin, with most towards the line corresponding to v sub 2. Sinks are called stable equilibria. Now, let's say that both eigenvalues are positive. Then the origin is called a source. In particular, if lambda sub 1 is greater than lambda sub 2, then all solutions tend to infinity, where most follow from the line corresponding to v sub 2. Sources are called unstable equilibria. Finally, let's say that one eigenvalue is positive while the other is negative. Then the origin, our equilibrium point, is called a saddle. Note that saddles are neither stable nor unstable because they depend upon the direction you use to approach the equilibrium point. Today, we're going to generalize this a little bit and talk about complex eigenvalues. We'd like to consider a two-dimensional linear system with constant coefficients, just like before. Here, we'll express this in terms of a 2 by 2 matrix A. Recall that we found earlier in the course that any functions y sub t and x sub t and y sub t, which are solutions to this two-dimensional system, must also be solutions to a second-order differential equation. Here, we can express the coefficients p and q in terms of the coefficients of our 2 by 2 matrix A. We found last time that if the 2 by 2 matrix A has distinct eigenvalues, then the general solution to our two-dimensional system can be expressed in terms of straight line solutions. Now, we know that we can express the eigenvalues as roots of our characteristic polynomial. And we've already seen that the eigenvalues, lambda sub 1 and lambda sub 2, are real numbers if and only if the discriminant p squared q is non-negative. But what happens if the discriminant p squared minus 4q is negative? Let's consider a special case to get an idea of what might happen here. Let's consider the matrix A, 0, 1, minus 1, and 0, which has the characteristic polynomial lambda squared plus 1. In this case, will involve square root of minus 1. We'll use this to make some definitions. We call the symbol I, namely the square root of minus 1, an imaginary number. If a and b are real numbers, we will call the symbol a plus bi a complex number. We'll denote the collection of all complex numbers by a bold letter C. We'll say that A is the real part of the complex number A plus BI, and we'll denote this by RE of lambda, where lambda is this complex number. Similarly, we'll say that B is the imaginary part of our complex number lambda, and we'll denote this B by IM of lambda. We note that we can add and multiply together complex numbers. For example, if we're given a complex number Z, which is A plus BI, and W, which is C plus DI, we can write Z plus W as having the real part A plus C and imaginary part B plus D. Similarly, Z times W has real part AC minus BD and imaginary part AD plus BC. Given a complex number lambda, which is A plus BI, its complex conjugate is A minus BI. Its norm, which we'll write here as the absolute value of lambda, is the square root of A squared plus B squared. Observe that lambda times its complex conjugate is equal to A squared plus B squared, which is just the square of the norm. Finally, let's say that Z equals A plus BI is a complex number, and W, which is C plus DI, is a non-zero complex number. Then we can consider the quotient Z divided by W. The idea is that we take a look at the process of multiplying the complex conjugate W bar on the numerator and denominator. We can then multiply out the numerator, Z times W conjugate, and we can multiply out the denominator, W times W conjugate. So the quotient Z over W is again a complex number, although the expression here is a little bit more complicated. I'd like to remark that we can also express the real part of a complex number lambda as lambda plus its conjugate divided by 2, and the imaginary part of a complex number lambda as lambda minus its conjugate divided by 2i. Now, a 2 by 2 matrix A may have eigenvalues A plus BI, which are complex numbers. Still, there are straight line solutions, capital Y, which is e to the lambda t times an eigenvalue v plus an equilibrium point y sub 0. We have here a motivating question. What is e to the lambda t when lambda is a complex number? We can answer this using what's called Euler's identity. Let lambda equal a plus bi be a complex number. Then e to the lambda we can express as e to the at times the complex number cosine b plus I sine b. We'll explain why this is true. Let's consider an initial value problem, dy dt equals a times y, where y of 0 equals the vector 1 comma I, and we're specifically going to choose our matrix A to be A, B minus B, A. The idea of our proof is to provide two solutions to this initial value problem and thereby use the existence uniqueness theorem to show that these solutions must be equal to each other because the solution to our initial value problem must be a unique one. It's easy to check that the eigenvalues and eigenvectors for this 2 by 2 matrix are lambda 1 equal a plus bi and v sub 1 being 1 comma I. This then yields our two solutions. First, from the straight line, capital Y of t is e to the lambda t times v sub 1, or we can write down a completely different solution, u of t, in terms of e to the at and cosine bt. All the one has to do now is just check that both of these vector valued functions satisfy the initial value problem above. Therefore, y of t equals u of t, and we can use this to now deduce Euler's identity. We'd like to discuss how does one obtain real valued solutions from complex solutions. Indeed, we have introduced complex numbers and hence complex valued functions, but we'd like to only focus in this class on real valued solutions. Let's consider a two-dimensional system where our 2 by 2 matrix A has distinct eigenvalues lambda sub 1 and lambda sub 2. Assuming that, of course, we have complex eigenvalues, we know that there exist real numbers alpha and beta such that lambda 1 equals alpha plus I beta, while lambda 2 equals alpha minus I beta. That is, lambda 1 and lambda 2 are complex conjugates of each other. Second, the only equilibrium point, y sub 0, is the origin. Third, let v sub 1 be an eigenvector associated to our eigenvalue lambda sub 1. Then its complex conjugate, v sub 1 bar, is an eigenvector associated to the eigenvalue lambda sub 2. Finally, let's consider the two real valued functions y sub re, which is the real part of y sub 1 of t, and y sub im, which is the imaginary part of y sub 1 of t. These are both in terms of the complex valued function y sub 1 of t, which is just a straight line solution. Then the general solution to our two-dimensional system can be expressed as capital Y equals C sub 1 times Y sub RE plus C sub 2 times capital Y sub IM. Let's explain why this is true. First, by looking at the characteristic polynomial of our 2 by 2 matrix, we can explicitly write out the eigenvalues lambda 1 and lambda 2, and we do indeed see that we can express them in terms of real numbers alpha and beta. Now we'd like to show that the origin is our only equilibrium point. Let's assume by way of contradiction that this is not true, that there is a different equilibrium point. Then this means that the determinant of our 2 by 2 matrix must be 0, and so we're able to conclude that both alpha and beta must also be equal to 0, thereby showing that lambda 1 equals lambda 2. This of course contradicts the assumption that our eigenvalues were distinct complex numbers. Let's say that v sub 1 is an eigenvector for our eigenvalue, lambda sub 1. We're going to show that v sub 1 conjugate is also an eigenvector for lambda sub 1 conjugate. Here we see that lambda sub 2 times v sub 2 is just the complex conjugate of lambda sub 1 times v sub 1, but because v sub 1 is an eigenvector, this is equal to the complex conjugate of a times v sub 1. But now, A is simply a real matrix, so it's equal to its own conjugate. V sub 1 conjugate is by definition V sub 2, so we're able to conclude that A times V sub 2 is equal to lambda 2 times V sub 2. Finally, we'd like to take a look at the general solution of our two-dimensional system, but in terms of real valued functions. We know, to begin with, that the general solution of our system expressed in terms of y sub 1 and y sub 2, where y sub 1 is a straight line solution and y sub 2 is its complex conjugate. Let's now express both of these functions in terms of its real and imaginary parts, that is capital Y sub re and capital Y sub im. Then, by simple substitution, we find that capital Y we can express in terms of capital Y sub re and capital Y sub im. We're going to use this now to end by explaining an algorithm that will allow us to solve any two-dimensional system where we have complex eigenvalues. Let's assume here that q does not equal to 0 and p squared minus 4q is less than 0. First, we'll compute the eigenvalues lambda sub 1 and lambda sub 2, as well as eigenvectors v sub 1 and v sub 2. Recall that lambda 1 and lambda 2, as well as v1 and v2, will be complex conjugates of each other. Second, let's compute the real and imaginary parts of the straight line solution y sub 1. That is, we'll compute here capital Y sub re and capital Y sub im. Both of these will compute using Euler's identity, that is e to the lambda t, we can write in terms of e to the alpha t, cosine beta t, and sine beta t. Finally, we'll write the general solution, capital Y, in terms of capital Y sub re and capital Y sub im. We'll use this here to make a few definitions. The equilibrium point, namely 0, 0, is called a center. If alpha is negative, we'll say that our equilibrium point is a spiral sink. If alpha is positive, we'll say that our equilibrium point is a spiral source. And if alpha is equal to 0, we'll say that our solution, capital Y of t, is a periodic solution. The quantity 2 pi over beta is called the natural period because capital Y of lowercase t plus capital T is equal to capital Y of lowercase t for all time t. The reciprocal 1 over t, that is beta over 2 pi, is called the natural frequency, whereas 2 pi over t, namely beta, is called the angular frequency. We'll end things today by going over one example to put all of this together. Let's consider the following two-dimensional system where capital A is -2, -3, 3, and -2. We'd like to compute the general solution, capital Y, in terms of capital Y sub RE and capital Y sub IM. In our first step, we'll compute eigenvalues and eigenvectors. We find that lambda sub 1 is -2 plus 3i, and v sub 1 we can choose as I, comma 1. That is, alpha is equal to -2, while beta is equal to 3. Second, we'll compute real line solutions. That is, capital Y sub 1 equals e to the lambda 1 t times the eigenvector v sub 1 plus the equilibrium point y sub 0. Here, we'll remember that e to the lambda t we can express in terms of Euler's identity, and we find e to the -2t times cosine 3t plus I sine 3t. We'll also plug in the eigenvector I, comma 1, and we'll plug in for the equilibrium point just the origin 0, comma 0. Third, we'll return our general solution in terms of the real value functions capital Y sub RE and capital Y sub IM. Here, we're just looking at the real and imaginary parts of the straight line solution from above. And finally, we recall that since alpha equal -2 is a negative real number, then our equilibrium point must be a spiral sink. Thanks very much for watching.